All right, Mr. Simpson back here with our second video for chapter 13, 13.2 equilibrium constants. Please pause the video and copy down your learning objectives. In this section, we're going to talk about the equilibrium constants, and we're going to take a look at some quantitative relationships here. So just as a review here in our generic equation, the capital letters are going to refer to our substances, elements, compounds, molecules, and the lowercase letters in front are going to refer to the coefficients that we would be using in a balanced equation. Okay, so here are our expressions, and I actually have two written for you. One for what's known as the reaction quotient, that's the Q. And the other that's the equilibrium constant. And that's the K. You'll see here that both of them have a subscript C, and I'll talk more about that in a second. Okay, it has to do with the fact that we're going to be comparing concentrations here. Okay, so the reason why I've given both of these to you at the same time is because the process of setting up the expression for both is exactly the same. All right, the difference between the reaction quotient and the equilibrium constant is going to allow us to determine which way our reaction is going. So remember here, our reactions are now reversible. Okay, so you're going to hear me say some important points here as we set up these expressions. The first one, as you can see here, is products over reactants. Okay, products over reactants. So we put the concentration of the products over the concentration of the reactants. Just a reminder that anytime I have brackets like this, that means concentration of. Okay, so products over reactants is the first part of this. That's why you see here we have our concentration of C and D over the concentration of A and B. The second part of the expression here is coefficients become exponents. Sorry, I'll keep that there so you can still see the expressions. Coefficients become exponents. So here you can see that the small letters in our balanced equation that represent the coefficients and the stoichiometric relationships here become the exponents in our expressions. So that's why I say coefficients become exponents. Okay. Now, this is the start of a long process dealing with various expressions that are going to be done the same way, right? So we have KC, we have KSP, we have KA, we have KB, and all these expressions are going to be set up the same way. So products over reactants, coefficients become exponents. Okay. The difference here between the QC and the KC is that if we're calculating K, then we know those concentrations to be equilibrium concentrations. Okay, we are calculating the equilibrium constant, so those are the concentrations that are occurring at equilibrium. Okay, so for K, concentrations must be those at equilibrium. Anywhere along the way, so either before we reach equilibrium or after equilibrium, if we set up this expression, we aren't solving for the equilibrium constant, we're solving for the reaction quotient. So anywhere along the way, not necessarily at equilibrium. Now, we could go into a problem not sure where we were and find out that we are at equilibrium based on the comparison between Q and K. But the big difference is going into the problem, if we know this system to be at equilibrium and I have concentrations, I would be therefore calculating the equilibrium constant. Somewhere along the way, I would be calculating the reaction quotient. Okay. The last piece of setting up these expressions, which will lead to the third thing you'll hear me say a lot. So products over reactants, coefficients become exponents. The third thing you'll hear me say is exclude solids and liquids. Okay, so we have two types of equilibria. We have homogeneous and heterogeneous equilibria. So this has to do with the state the reactants and products are in. Or phase, right? So just as you remember, so gas, solid, liquid, aqueous. Okay, two of those four are not going to affect the equilibrium at all. So really, it comes down to um, gases and aqueous solutions. Okay, so the last thing you're going to hear me say is exclude solids and liquids. So if I have an example of a heterogeneous equilibria, meaning I have a combination of different types of those phases, then pure solids and pure liquids do not appear in the K expression. All right, pure solids and pure liquids do not appear. So this is that last point you'll hear me say, exclude solids and liquids. All right, so I'm just going to change the color of these three things real quick because these are the key points that you will hear me say as I set up our expressions. Products over reactants, coefficients become exponents, exclude solids and liquids. So when I look at an equation, a reaction, that's how I'm going to set up our expression, whether we're setting up Q or K. The last thing I want to talk about here before we're getting close to doing a problem is this last idea that if everything I have is in gas phase, then I could actually solve for Kp. And the difference there is just simply what we plug in, right? So Kp is also a possibility. So the difference here would be I would be using pressures instead of concentration. So thinking back to if thinking back to our original reaction, if we had all gases and I wanted to solve for the data given to me were their partial pressures, then it would be the pressure of C raised to its coefficient times the pressure of D raised to that coefficient, and so forth as I set this up. So if they gave me concentration values, I'd be solving for Kc. But if they gave me pressures, then I would be solving for Kp. Again, setup and everything is the same. Products over reactants, coefficients become exponents. This is only going to happen in a gas phase solution, so everything is gases. So you don't have to really worry about that last part. So the difference there is I would be solving for Kp instead of Kc, or again Qp instead of Qc if we're given pressures instead of concentrations. All right, so what we really want to do is start to compare these values and get a sense of which way our reaction is going. So before we start to compare Q and K, let me first just talk about the magnitude of K. So if K is very small, the mixture contains mostly reactants. So if we think about that, since it's products over reactants, if that is a small number, then that means the reactants is going to be larger, and so it's going to contain mostly reactants at that point in time. Obviously, the opposite case tells us that we have mostly products. So now let's think about the comparison between Q and K. So often what we'll end up doing, because we won't necessarily know if we're at equilibrium or not, is we will calculate based on the concentrations we have. We will be calculating Q, the reaction quotient, and then we will compare it to a known equilibrium constant. All right, so as I look at these three possible cases, obviously the bottom one is the easiest, right? So if Q, the value that we calculate, is equal to the equilibrium constant that they gave us, then we know this is at equilibrium. All right, so if those two values are the same, we know we are at equilibrium. Okay, so now if we calculate the Q and we find that it's less than the equilibrium constant that was given, we can think about what this tells us, right? So if it's even smaller, we said that small Q values tell us that we have mostly reactants. Well, if it's going to be even smaller than that, than our K value, then we have mostly reactants. That means that it is still shifting to the right. Okay, so remember, they can either shift to the right or I'll actually say forward, because you'll see it referred to both ways. Okay, so this is going to be moving, this reaction is going to be proceeding to the right or in the forward direction because we have more reactants if Q is less. Obviously, if we have the opposite scenario, then Q is greater. That means we have more products, so those products need to now get used up. So in order to get used up, they have to be on the reactant side. So that means our reaction is proceeding to the left or in the reverse or even sometimes backwards direction. Okay, so that's going to be our task here, or our goal as we do some calculations. Okay, so here's an example problem, and I will kind of walk through this for you, with you, and then we will be on to doing some practice problems on our own. Okay, so we want to calculate the reaction quotient and determine the direction in which the following reaction will proceed to reach equilibrium. So a couple things here that I want to highlight, and I chose this problem specifically. Okay, so remember our expression for the reaction quotient is going to be the concentration of the products. Coefficients become exponents over the concentration of the reactants. Okay, now be careful. So I picked this problem for a reason. They do not give me concentration in the problem. They give me moles. All right. So remember, concentration is molarity, and molarity equals moles per liter. Okay. So just be aware that if I may have to do some additional calculations. You even could have a situation where they give me grams here, right? So I'd have to convert to moles and then divide by liters. Now, had you not caught that in this particular problem, it wouldn't have been a problem because we're in a 1 liter flask. So the concentrations on all these are going to be divided by 1, right? So the concentration of NO is going to equal 0.0500 moles divided by 1 liter. So you're going to end up getting those values anyway. But I wanted to point that out just so you don't miss that along the way. Okay, so let's set up our expression now, assuming that I went through the process potentially of determining the concentration for each of these by dividing by 1. I would have a concentration for the NaCl of 0.5 molar, and that's going to be squared. Then our concentration of our NO will be molar squared, and our concentration of our Cl2. Okay. When I do this work, I'm actually going to get a value of 6.45 times 10 to the third. Now, Q and K values are unitless, so you do not need to worry about a unit here. And so now I'm going to compare this to the K value that was given in the problem. So you see over here, they gave me the K value. So since I have a situation here in which Q is less, you can see here that Q is less than K, and just to be perfectly correct, QC is less than KC, so this is going to be proceeding to the right. Q is less than K, it's to the right, or again, you could also refer to that as the forward direction. All right, so that's how we're going to be solving these problems. Remember the 3 important parts: products over reactants, coefficients become exponents, exclude solids and liquids. Now that last one didn't come into play here because I had a homogeneous equilibria in which all of my states were the same. Okay, and then the relationship between Q and K, and also don't forget, this data could have all been given to me in pressures, and I would have been solving for QP or KP. All right, that wraps up our second video here in Chapter 13. Now we'll get to some practice problems.